Hello everybody. I'm delighted to have Professor Dieter Suter from Dortmund University to give a lecture, the seminar series, FriQuant Seminar Series, organized by iHub Quantum Technology Foundation. So, this iHub Quantum Technology Foundation is a not-for-profit company being established by IISER Pune in IISER Pune through funding from the Department of Science and Technology, Government of India. It is similar to another not-for-profit company that is there on campus called as Atal Incubation Center, but that is more for uh, tech, setting up, enabling startups to develop products and small incubating these companies. Same thing with this particular organization. This particular company is going to enable development of technologies in the domain of quantum technologies, and in addition to uh, having in-house technology development through the PIs involved in this particular project from IISER Pune. So there are about 12 PIs from the institute who are involved in this project. Plus, we have many other committed collaborations from various parts of the country. So we have recently kicked off many of our activities, and one of the activities is a seminar series. Is this seminar series, and we are glad to have you here. I request Mahesh to please introduce the speaker, Professor Dieter.
Thank you, Makant. So, good evening, everyone. So, this is my pleasure to introduce Professor Dieter Suter again. Last week, I introduced when he was giving general lecture at the physics department. So now he is giving more specialized lecture on quantum technologies today. So this is for the benefit of those people who are not present last week. I am going to repeat what I said last week. So Professor Dieter Suter started his education in chemistry. He had diploma in chemistry, and then he decided to switch to physics. So he had habilitation in physics. That's the German system, I believe. And then he moved on to do his PhD in physics and spectroscopy with Professor Richard Ernst in NMR spectroscopy. That was in 1985. He finished PhD, and in 1991, Professor Richard Ernst got Nobel Prize. So then he moved on to advanced experiments in NMR spectroscopy. He moved on to solid state NMR, and then he joined Alex Pine's group in Berkeley, where he did very interesting experiments, physics experiments. He was the first one to observe geometric phase by NMR. And Alex Pines is another stalwart in the NMR field. And then eventually he joined the University of Dortmund, Germany, I think in 1995. And since then, he has been leading the experimental group E3 Dortmund, which houses many laboratories and many other faculties under him. And he has been leading since then. And his own interests are very diverse. He's working on NMR spectroscopy, ESR spectroscopy, MRI imaging. In the last presentation, he talked about imaging also. And also, most recently, he started working on quantum information by spins. And when we talk about quantum information by spins, there are various architectures, not just NMR. One can use nuclear spins in NMR, or one can use electron spins in other architectures. Today, he is going to talk about hybrid. So, how you can use hybrid architectures for quantum registers. Yeah, so I just want to add that he is also a popular teacher, and so he has been visiting India many times. He has given colloquia at IISER Pune previously. So it's a pleasure to have you here again. And currently he's visiting IISER Pune as the DST Vajra faculty. As you know, Vajra faculty is an award for eminent scientists who can visit India, interact with faculty, students, set up collaborations, and start building networks and so on. So that's the program. He's here, and he'll be here for 1 more week, and I welcome students to approach him and interact with him. He'll be here in the physics department for another week, roughly more than so till the end of the next week. Okay, so with this introduction, I request Professor Dieter Suter to begin the lecture.
I assume I should use the mic, right? Okay, can you hear me? Good. Yeah. Again, it's a real pleasure to be here, or to have been here. It's almost over now. And I would like to thank, of course, Mahesh for the very nice introduction. And I would like to talk a little bit about our work on hybrid quantum registers. Actually, I have to correct you in one respect. It's not our most recent interest, because we started doing that 23 years ago. Not exactly this type, so I'm not going to talk about the old stuff, but more about recent stuff. Of course, it's really quite different from what I talked about last week. Completely different subject, but I would like to try to be not too specialized. I'm not quite sure what your background is. I will assume that you know basics of quantum information, but maybe not everybody is an expert in magnetic resonance. That was basically what I thought I would take as a level. And let me introduce the location where I come from. I don't know if, well, I know Mahesh has been in Dortmund, but he might be the only one in that room. Oh, okay. Right. Yeah, you know it well, of course. So Münster is actually about here.
Neighbors.
Pretty close, yeah. Anyway, it's a medium-sized city in the northern part of Western Europe, I would say. This is an image from the center of Dortmund, and this is an aerial view of the campus of our university. This is the math tower of the university. So the campus has two parts, the south and the north part, and it has roughly 35,000 students. So it's a bit bigger than IISR. It's not the full university. It calls itself a technical university. That's what the TU stands for technical university. So we have no medicine, we have no law school and so on. Anyway, yeah, so before I start with the actual topics, I would like to introduce the people who did most of the work. And as you may notice, there is a clear dominance of India here. I start with Jingfu Zhang. He's from China. And then we have a bunch of Indians. Koti, he's now at Bennett University in near Delhi. Swati, she recently joined a startup company in quantum computing. Tanmoy, I think he's right. So she was from ISR Pune. Tanmoy also, right? Or no, he spent some time here, but he didn't come from here. Yes. And then there's Harpreet Singh, who's from another IISR, from Mohali. And finally, there's one German student, Alex Holberg. He's just about finishing his master's thesis. These four people work on diamond. That's the main topic, but I also want to introduce a little bit what these two guys are doing. That's silicon carbide, so I'll briefly mention that. As I said, I will assume you are familiar with the concept of quantum information processing, but I'll just introduce it anyway. The general concept, we are all working with the so-called network model, which means that you need a quantum register, which has hopefully a large number of qubits or quantum bits. And to use that processor, you need to initialize, and I'll go through these steps then one by one. You need to process the information, and in the end, you have to read out the result. That's general for any type of quantum computer. And the requirements are that you can make something useful. You need as many as possible qubits in this quantum register. We're actually going to look at relatively small numbers, but that's enough for giving the principles. You have to be able to apply specific operations to individual qubits or pairs of qubits, and together that forms a universal set of gates. That's what you need. Now, as the title says, I want to talk about hybrid qubits or hybrid quantum registers, which means that we will combine different types of qubits. So very often you use a quantum register which has one type of qubits, for instance, just photons or just ions. That's of course convenient, and most people are expert on one specific type of qubit, so they like to stick to those. And what I would like to advertise here is that sometimes there is no best qubit, but it's better and more effective overall to combine different types, because each type of qubit has its own strength, and you can use one type to avoid the weaknesses of the other type. And I'll show you what that means specifically. Now, let me introduce the main material that we use. That's this here. Well, not the woman, but the rocks on her necklace and so on. So diamonds. And says a girl's best friend, but you don't have to be a girl. You can also enjoy them if you're a man or a boy. So you know, of course, what diamond is. It's a crystal made of only carbon. That's pretty boring. I mean, it's great material. It's very solid. It has a high index of refraction, so you may find that interesting. But it's certainly useless for real applications. So the type of diamond that we use has some defects. Specifically, we use the so-called nitrogen vacancy defect, where two carbons are missing. One of them is replaced by a nitrogen, and adjacent to that you have a vacancy. So together that makes an NV center or nitrogen vacancy center. And in general, if you have diamond, the really valuable ones are not the perfect crystals, but ones which have some types of defects. They make the colors, for instance, and they make them valuable. So the most valuable diamonds are not the colorless ones, but the colored ones. And that's the same is true for many other applications, like, for instance, quantum information processing. And it's actually this yellow type, which is basically due to the NV centers. Now, the reason we need that is that in the NV center, you can scatter photons. So they can absorb photons and they can emit photons. And if you look at them, you have 5 electrons here with together combined into spin 1/2 state, and it emits photons in this spectral range. Now, we're not really looking at this one. We're looking at the negatively charged NV center, so it captures another electron. So you have a negative charge, that's a so-called NV minus center. Normally, one doesn't mention the minus, but when you read the literature, NV normally means NV minus. And so that's the PL spectrum of NV minus, which has a total of 6 electrons, which combine to a spin 1 state. And to work with that, we need to optically excite it. I'll show you exactly what the optics does, but for this purpose, we need a so-called confocal microscope. That means we have a laser which is reflected on a dichroic mirror, focused by a microscope objective down to the diffraction limit. And in the center or in the focus of that beam, you have your NV center. It's excited into an electronically excited state, and then it emits a photon. That photon is, as you've seen, redshifted compared to the green laser. So it goes through this dichroic mirror, is collected by a lens, put through a pinhole, and then goes onto a single photon detector. The reason we use this pinhole is That's what makes it a confocal microscope. You select basically in the third dimension which part of the crystal you want to look at. So you confine the focus, and that means you reduce by orders of magnitude the background signal. So the photons that you reach have a much higher probability to be emitted by the center. And that's very important because you don't have that many photons. You have to avoid stray photons and scattered photons. So that allows you to measure, for instance, here a cross-section through a diamond crystal, and basically each of these yellow dots corresponds to an NV center or a few NV centers. You see the scale here is 10 by 10 microns, so you normally have, this is a very pure diamond already, that's why you can see individual centers. If you go closer, so you see a single center, but of course this is limited by the diffraction of the light. So the cross-section of this image is about half a micron. And in half a micron, you cannot be sure that you have a single center, which is important if you want to do this type of experiments. I'll show you in a moment how we can be sure. But before I do that, I would like to introduce the other material I already mentioned, silicon carbide. Silicon carbide is in many respects similar to carbon. It has the same structure, so you have tetrahedral environment, which is not too astonishing. I mean, one of the atoms is also carbon, but every second is replaced by silicon. But silicon is isoelectronic to carbon, so they gave the same structure. It's basically diamond structure, but alternating between silicon and carbon. So it's very similar. It has similar properties. For instance, you can also use it for making necklaces. It's also very hard. It has similar electronic properties. It has a large band gap, almost as high as diamond. But it is much more complicated. Just the fact that you don't have one type of atom, but two types of atoms makes it very much more diverse. For instance, you have about 250 so-called polytypes. I don't have any overview. I just work with two different polytypes, but there are quite many. And within each polytype, you have a number of different defects, and that can be useful for some applications because, because it gives you a bigger selection. For instance, some of these defects appear to be interesting for quantum information processing, others for sensing, and others again for quantum communication. For instance, there are defects which emit into one of the telecom bands. So it's more interesting if you want to couple so-called flying qubits to sitting qubits. And it's much less explored. So here we're just at the beginning of learning what you can do with this material. So this shows you a little bit what these polytypes means. This is so-called 6H silicon carbide. 6H means there are 6 different layers before the unit cell repeats. So there is a definite direction, that's the z-axis, and then you have here 6 layers labeled CB, CA, CB, and then the unit cell repeats itself. There are others like 4H, for instance, with which we work. You see here silicon and carbon, different layers. So the center that we look at here is the so-called silicon vacancy. So we have a missing silicon, which means we have 4 neighboring carbons. Again, it carries an additional electron, which means that it has a total spin 3½ in this case. There are different sites, so the environment can be different. Depends if the silicon that is missing sits here or this layer or this layer. It can have a hexagonal environment or a cubic environment. Again, it has a z-axis, and the electronic structure, as I said, is a spin 3½ ground state. you can excite it into a spin 3/2 excited state. And if you then, if you let it absorb laser photons, that results in optical polarization, because there is also a shelving state. That's a spin s equal 1/2. And what happens is, if you excite it, some of the atoms fall into this shelving state, and from the shelving state there is a bigger probability that it goes into these plus or minus 1/2 states than into the 3/2 state. So if that repeats a few times, you get a bigger polarization, bigger population in this substate. So you generate spin polarization in the system. And I'll show you the similar process in the diamond afterwards. Of course, in principle, it can also fall down here, but this is much less likely. And so that's how we get the spin polarization. Now, here also you see a confocal microscope scan of such a sample. In this case, you see a regular array of centers, and most of these centers are single centers. Some of them are double or triple or some other defects, like here. Obviously, this is much too bright for a single center, but this has been generated by ion implantation into that sample. So what I'm going to show you now are two specific centers. This one, I'll show you some optically detected magnetic resonance, and I'll show you some results from this one, where we do a so-called G2 experiment. What's this G2? I'll start with that one. G2 is a correlation experiment which is designed to find out if it's a single center. I mean, I told you we believe that this is a single center, for instance. Here we're not quite sure. So if we want to work with a single center, we have to make sure it's really a single one. And that's what these so-called anti-bunching experiments do. What one does in such a G2 measurement is you measure the probability to detect a photon immediately after the previous photon. So how likely is it here in this case, for instance, when you have measured a photon, that the second one arrives right afterwards? Now, if it's a single atom or a single center, then the probability is 0. Why? Yeah?
Is there any specific reason those two specific centers are selected for these two experiments?
I mean, you have to select one.
So it's like random, no, just less bright centers than.
Yeah, we could take another one if we verify that it's. I just wanted to show from which one I took the results. We did more than one, but I just wanted to show that you can select the center and then you do your experiments on that one. Well, if I take this one, for instance, then it probably will turn out that it's not a single center. So we took such ones where the number of photons per unit time was of the right order of magnitude. That increases the probability that it's a single center. Yeah.
Now, since you are already disturbed, so is this a laser scanning image, or you are scanning the stage?
We scanned the stage. Well, actually, yeah, the microscope objective. So the microscope objective sits on the nanopositioner. The crystal sits on a micropositioner. So if we have bigger movements, then we move the crystal. But for these images, we scan the nanopositioner, which holds the microscope objective.
What's the typical numerical aperture for the collection?
In this case, I think about 1.3. In the diamond, I think it's 1.4. But this is order of magnitude. We normally don't go for the very highest ones because we need a little larger working distance. So typical working distances are on the order of 150 microns. For instance, we have a wire in between.
And this is all at room temperature?
Yes. We have so these single center experiments, they're all at room temperature diamond also, but on ensemble experiments on silicon carbide, we also have done low temperature experiments. But I'm not going to show that.
Yeah, because you said the working distance is just a few hundred microns, so I would be wondering how you do low temperature experiments there.
Yes. No, that's why I'm saying those we did with ensemble measurements. So the working distance was, I mean, there we had a normal lens, not a microscope object.
That makes sense. Thank
Yeah.
you.
Anything else? Okay. So, as I say, if you have a single atom or ion, if it emits, or center, if it emits a photon, then it's the ground state, and it cannot possibly emit the second photon immediately. It takes some time, it has to absorb energy again from the laser to go to the excited state, and then it can emit photons, and that's, you see exactly how long it takes to go back into the excited state. That's the time constant here, which is on the order of 5 nanoseconds or so, or 3 nanoseconds. Now, here we measured, and the condition to have single center is that here it drops below 0.5. So this is the normalized correlation function. If it goes below 0.5 at 0, then it's a single center. If you have 2 centers, it goes to 0.5, and 3 centers go to 0.67. Anyway, so you see 2 curves here. One was measured with 10 microwatts of laser power, and the blue one with 1.4 milliwatts. And there is a significant difference here. You see that you also have an overshoot for intermediate times, and this is so-called bunching. So here the probability to detect the second photon is actually bigger than for long delays. And that's indication that it's a single center, but it has more than 2 energy levels. And I'll come back to that. You've already seen that. There is this so-called shelving state. And actually from this shape here, we can determine the rate constants for the transitions between these different levels. Yeah, and as I said, I'm going to show some results on optically detected magnetic resonance, ODMR. Again, from a single center, but from a different one. What we do here, we apply a radio frequency, we scan this radio frequency, and we measure the change in the photoluminescence that's emitted by this center. And so this is the signal from a single center, that's why it's a bit noisy. What you see here is a clear resonance. This is about 70 megahertz. And we see a second resonance here, which you may not believe if you see this noisy spectrum, but you will believe it in a moment. And this is a fit, so this is the result that we get. Now, it has only a single transition. This is known from literature to be the transition between the 2 spin states of the ground state in B equals 0, in a zero magnetic field. And it can be identified as a V2 center, whatever that is. Now, this transition here, which you may not yet believe, occurs exactly at half this frequency. And maybe you believe it now if you repeat the measurement with different radio frequency intensities. So the green line that I showed you first was measured with 110 milliwatts of radio frequency power. And then we increased that up to 1.8 watts. And you see that this transition grows more strongly than the transition near 70 megahertz. And this is funny. This is actually a 2-photon transition. 2 radio frequency photons are absorbed to make that transition, and that's why it depends more strongly on the intensity or the power of the radio frequency field than the main transition here. So it's a single spin which can absorb 1 photon or 2 photons. And we've actually seen it also can absorb 3 photons, and you can have transitions between, this is a 1 quantum, 2 photon transition. You can have 2 quantum, 3 photon transition, and so on. It's a really nice playground, but I don't want to waste too much time on that. So let me instead briefly show you how the experiment looks like. In particular, now again for the diamond setup, where we normally apply a magnetic field either with an electromagnet or with a permanent magnet, which is controlled then by these rotation stages, so we can apply a magnetic field in arbitrary direction and almost arbitrary strength. Almost arbitrary means well, in principle, the magnet goes up to about 1.5 Tesla, but we have to be far enough so that it's maybe 100 millitesla is realistic. And then the laser comes from the bottom. This is the microscope objective. This is the nanopositioner. And here we scan, this here sits on another micropositioning stage, which is not shown here for clarity. So the sample itself then, in this case a diamond, sits in a PCB board. These are microstrip lines, and in between here you see in this enlarged scan or enlarged image, we have a wire which we draw across the sample, and the radio frequency or microwave in this case goes, or both go along this wire, and that means we have normally to measure quite close to this wire because the fields are quite inhomogeneous, but there are normally enough centers in the vicinity of that wire. So we're back now to NV center diamond, and I would like to show how this works in practice. So we have a ground state, which is a triplet A2 state. So it has a spin 1, and it has a so-called zero field splitting. That means in the absence of a magnetic field, the ms equals 0 state is energetically lowest, and the ms equal plus and minus 1 states are slightly higher. The same is in the excited state, which is a triplet E state and sits around 2 electron volts above the ground state. Now, to work with that, you apply laser, normally non-resonant, so typically about 2.2 electron volts, 10% above the transition frequency. So you hit some excited state, but the system quickly relaxes into these states. Now, let's first check what happens if the center is initially in ms equals 0 state. The transition itself is spin conserving, so it goes into the ms equals 0 state of the excited state and then falls back. Basically, nothing interesting happens, except that you convert the laser photon into a fluorescence photon. It's different if you're initially in ms equal plus 1 or minus 1. It also goes into the ms equal plus or minus 1 state of the excited state, but then it can happen that the system crosses over from the triplet manifold into the singlet manifold. So there are 2 singlet states over here, and this transition is of course dark, so there are no photons emitted, and it takes some time until the system cycles through these 2 singlet states and back into the ground state. Now, of course, as it goes over into the singlet manifold, it forgets that it was in the ms equal plus or minus 1 state. So it loses its memory, and it has a high probability to go over into the ms equal 0 state. So that means this cycle has converted some spins from ms equal plus or minus 1 to ms equal 0. And just as in the case of the silicon carbide, we basically initialize the system into the ms equal 0 state if we irradiate it with light. You can actually measure that even with conventional EPR. You just see the polarization here increases if you apply basically any light.
Sorry, can I ask why that first transition was dark? I missed something.
Oh, this is, it's a conversion process from triplet to singlet. So that doesn't generate, I mean, it would correspond to a far infrared energy, but I think this is probably mostly non-radiative. In principle, this is an infrared
The spin has to go from 1 to 0, right?
Right. Mm-hmm.
So it must emit something. I mean, what?
Yeah, but it's probably coupling to the lattice.
I see.
I mean, it anyway has, because, you know, for it to happen, you need some symmetry breaking. And that symmetry breaking is non-radiative. At least nobody has seen it. This transition you can actually excite, but I don't think people have been able to observe photons from it. And with our detector anyway not, because this is, I think, about 1 electron volt, and we cannot see anything beyond 1.5. And the same for this transition. Okay, so this cycling populates the MS equals 0 state. And that's important for our quantum information applications, because to do quantum information processing, you have to generate a pure state. So you have to initialize your system into a specific state, and that is normally this MS equals 0 state. You just shine a green laser for a few microseconds, and the system is polarized here. So that's one way how the laser is used here, and it's also used for detection. As I said, this process here is non-radiative, and it takes time. I mean, falling back here takes 10 nanoseconds, whatever the lifetime of this excited state, on the order of a few nanoseconds. This process here takes microseconds to milliseconds. So if you start initially in MS equal plus or minus 1 state, and then you shine a laser pulse, collect photons, on average you will collect fewer photons for MS equal plus or minus 1 than for MS equal 0. So just by counting photons during a laser pulse, you can determine what the state of the system was before you applied the laser pulse. Unfortunately, or fortunately, this, I don't know, that depends on what you want to do. This is a destructive readout. So because it always puts the system into MS equals 0, you cannot just keep reading out. Normally the best is the readout process should take less than 1 microsecond, otherwise you lose signal to noise. But anyway, you can read out the system with a certain probability, yes.
Sorry, I missed some point. So the singlet states, they also exist in this system already?
Yes. Yes. Okay. So, as I said, you have a ground state. So here I'm looking now just at the electronic ground state. And the zero field splitting is about 2.87 gigahertz. And this transition you can excite by applying microwaves. If you also apply a magnetic field, then the degeneracy between these two levels is lifted, and you get actually 2 transitions which are split by twice the Larmor frequency. And yeah, so these are the so-called allowed transitions in a simplest approximation. And that allows you now to generate gate operations on the electron spin. I mean, you can define your qubit by choosing, for instance, these 2 states. One of them you call your logical 1, the other one is 0, and then you apply a resonant microwave field and generate a rotation on the Bloch sphere of this 2-level system or qubit. And you can just adjust the frequency, the amplitude, the phase, the duration of these microwave pulses, just as the experts do it in NMR, quantum information processing. So this is a system which can be controlled very precisely, very easily, and has been done very successfully for many years. Yeah?
Can you go back, please? One slide. Yeah, so in those transitions, those 2 transitions, those are circularly polarized microwave transitions?
No. This is, I mean, it has a C3 symmetry, and so there is no angular momentum, is not a good quantum number for the system. Z component is, but the transverse component are not. And so the whole also for the laser, you don't need polarized light. There is a certain polarization dependence, but it's not useful for initializing the system. And the same for the microwave pulses. Well, I mean, you're right in principle. So you could use circularly polarized light in microwave, but nobody does.
Because I mean, there's a spin change of plus or minus 1. So.
Yeah, but you would have to apply it exactly along the z-axis, which you normally can't do. And anyway, you don't have, because you're not using a resonator, but a wire.
Probably it doesn't matter since it's in the near field regime.
Not really. Well, no, you're right. Yes, it's in near field regime. Yes.
Basically, it selects one of the polarizations.
Yeah. Yeah. And we've actually had one case where we would have liked to. What's happening here? Okay. Anyway, no. So you're right. It's in principle they're circularly polarized. Okay. Yeah. So this was the concept, and so the whole experiment looks, for instance, like this. You initialize the system with a laser pulse into the ms equals 0 state. Then you apply your microwave pulse, for instance, on this transition, and then you read out the state of the system by another laser pulse. You count photons during this pulse, and it tells you if the system is in the ground or an excited state. And then if you do that, for instance, as a function of the duration of this gate, which means the microwave pulse, you count photons as a function of the pulse duration. You see, of course, Rabi oscillations. As you would expect, the system goes from logical 1 to logical 0, very much like in NMR. There's one major difference compared to NMR, because we are working with a single spin. There is no inhomogeneity. The microwave field is terribly inhomogeneous. I mean, it drops off over a few micrometers, but you're only probing it at a single location. So there is no inhomogeneity, and you see there is a certain decay here over a period of microseconds. A typical gate operation takes nanoseconds. So these are very long pulses, and the decay is quite slow, and it's due to dephasing processes from nuclear spins mostly. And the fidelity of a single qubit gate operation here is on the order of 99% or better. So that's why the control is pretty good. You can, of course, also, instead of applying one long pulse, you apply two short pulses. What these do, the first one excites coherence in this transition, then you have free precession. So in principle, you generate a free induction decay. Now for the NMR people in the audience, normally when you measure a free induction decay, you just turn on your ADC and measure the signal. This we cannot do here, unfortunately, because we only can count photons which are proportional to populations. So we measure longitudinal components or populations, and that's why we have to apply a second pulse here, which converts coherence back into population, which we then count with this laser pulse. So if you measure an FID, you have to vary the duration between these two pulses, and what you see then here is such oscillation decay, which looks very much like an FID, which it isn't, except of course here you call that a Ramsey fringe experiment, which is a term which was introduced in optics, where people also don't measure transverse don't always measure transverse polarization, but longitudinal ones. So this is what you measure, and obviously this is not a single qubit or not a two-level system. We see more than one frequency component, and you find out what's happening here. If you do a Fourier transform of this signal, you get essentially 6 resonance lines in this specific case. I have to emphasize here, in principle, of course, you have NV center, but every NV center is slightly different. The main reason is that you have nuclear spins around it. you always have a nitrogen spin. And in addition, you have, of course, many, many carbon spins. Now, most of the carbons are carbon-12, which don't have a nuclear spin, so they're not visible. And in fact, we actually use mostly, so this is a crystal with natural abundance. So in that case, 1% of the carbons are carbon-13, which have a spin of 1/2, and they have an interaction with the electron spin. Now, that's called hyperfine interaction. Now, in most cases, we actually use crystals which are purified in the sense that we have not 99% carbon-12, but 99.999%. So we only have like 10 ppm of carbon-13, which makes the lines a lot narrower, and we still find enough carbon-13 to use them as qubits. Anyway, so what you see here are a triplet first, that's due to the nitrogen spin, which has a spin 1, with a hyperfine interaction of about 2 megahertz. And then you have a second splitting due to a carbon-13, which is about 250 kilohertz in this case. So we have the electron spin, we have a nitrogen nuclear spin, and we have a carbon-13 nuclear spin. And this is the hybrid quantum register that I had in my title. I know my time is already up, almost up. So how much time do I have? An hour?
Yes.
Oh.
How much time do we need now?
Yeah, okay. Mm-hmm. So this is the hybrid quantum register that I had to cover at least. And we'll see how much time I have to actually discuss it. But the main point is that you can use these nuclear spins as qubits. And sometimes there are more. As I said, this is a random process. Sometimes you find a center which has many carbons. Like in this case, we have, again, a single electron spin, but we have many lines. And it can be analyzed. You have one carbon which has a hyperfine interaction of 8 megahertz. So the strength of the hyperfine interaction depends on at which position it sits, how far away it is from the electron spin. So the second carbon here has a hyperfine interaction of 5.8 megahertz. Then we always have the nitrogen, which always has the same hyperfine interaction because it's always at the same position. And in this case, we have a third carbon, which has about 0.4 megahertz hyperfine interaction. So in this case, you have quite a significant quantum register with which you could work. So if you want to use now not only the electron spin, but also the nuclear spin, you again have the problem that you have to initialize your system. You have to put it into a specific initial state. That's maybe the main advantage of this system compared to an NMR system. In an NMR system, you just can wait until you have thermal relaxation, which typically takes a few seconds, and then you have a thermal state. Here we can put the system into a pure state, and we can do it within a few microseconds, as I will show you. So let's look at the moment at a simplified system, 2-qubit system. We have one qubit is the electron spin that's labeled here with 0 and 1. And then we have a nuclear spin, can be either a carbon-13 or it can be 2 levels from a nitrogen-14. And the state of this nuclear spin is given by these arrows, which can be up or down.
Did you also use N50?
No, we don't, but some people do. It's, of course, more complicated, more expensive, but it has the advantage if you implant your NVs, you can implant N15s, and then you know that they're not background atoms, but they're the implanted ones.
So they are not quadrupolar, maybe with longer coherence time?
No, it's not. Well, it could be because you don't have quadruple interaction. Yeah. Mm-hmm.
I don't know, hyperfine.
Yeah, but I mean the nuclear spin coherence times are even so much longer than the electron, so it doesn't really matter. I mean, in some cases, it wasn't possible to measure the relaxation times of the nuclei at low temperature. They're probably weeks, and nobody has enough time to measure for weeks. to determine those relaxation times.
You mean T1?
Yes. Yeah, but T2, I mean, depends on how pure the system is, can in principle be close to T1 if you have a really pure system. Anyway, so yes, we want to initialize now both qubits into one specific state. So first of all, we start again with a laser pulse. Now the laser pulse, as I told you, initializes the electron into the ms equals 0 state. But it is not affected by the nucleus, or the nucleus is not affected by the laser pulse. So the nucleus is at thermal equilibrium, which means you have both up and down at same probability. So this is not fully polarized, or actually the nucleus is fully depolarized. If you want to initialize that one also, we can use pulses. For instance, because of the hyperfine interaction, the two EPR transitions, so this is one EPR transition, this is one EPR transitions, they are at different energies. So we can apply a selective electron spin microwave pulse, which drives this specific transition. So we flip we flip the electron spin with the microwave pulse. The nucleus spin stays, but then we apply also a radio frequency field, which flips the nuclear spin. So what we have now is the nucleus is fully polarized, while the electron spin is fully depolarized. Unfortunately, I mean, we cannot reduce the entropy in the system with microwave or radio frequency pulses, so we can only exchange polarization. But then we can now again apply a laser pulse. So we apply a second laser pulse, which again brings the electron into the ground state, and now both spins are fully polarized. At least in principle, that's the idea. And let's see how that works out. So the idea is we polarize the electron, then we swap the electron and the nuclear spin, and then we apply another laser pulse to repolarize the electron. That's the idea. And now let's see what happens. So this is the full system. In this case, we consider the nitrogen-14, that's the Mi, and the electron, which is labeled with the Ms state. And what we want at the end is both in the 0 state, so we want to polarize or bring the system into this specific state. So what you see here, the result, we want to get the population of this state as a function of the laser pulse duration of that second laser pulse. And ideally, before I apply the laser pulse, the electron is depolarized, so we have 1/3 population in these 3 states. And as you apply the laser pulse, they should go down to that ground state. So we would expect that the population of this state starts with 1/3 and increases towards 1. Now, in the experiment, it initially looks pretty good. So it increases as we want, but then it goes back down. And so this is the population of this state. And what apparently happens is that the laser pulse also depolarizes the nuclear spin. So it brings population from this state over to here. And you can verify that by measuring also the other populations. Both of them are initially 0, and then they grow. And for very long pulses, you see it's all, the electron is all in the ground state, but the nucleus is fully depolarized. So apparently I told you something wrong before. I said the laser pulse does not affect the nuclear spin. Well, to a first approximation, it doesn't. I mean, it does not, the absorption, for instance, does not depend on the nuclear spin. However, what happens is there is a hyperfine interaction between the electron and the nuclear spin. And as you absorb photons, you change the electronic configuration. You go to the excited state, which has a hyperfine interaction which is different from that of the ground state. And something even worse happens, because you can also have intersystem crossing that I mentioned. That's important actually for polarizing. And if you go to the singlet state, obviously the hyperfine interaction is gone. So it's a modulation of the hyperfine interaction. And if you, in addition, you can have ionization. I told you we have different charge states of the NV center. And this ionization process is, of course, change the electronic structure, modulate the hyperfine interaction, and this creates basically a random field on the nuclear spin, which makes it forget its polarization. And what happens here, this ionization process is the following. We have the NV minus, which sits in the band gap between the valence band and the conduction band with 1.95 eV between the two states. We excite that, so the resonant transition energy is 637 nanometers, but we excite it with a green laser, and that green laser can ionize it, so the extra electron goes over into the conduction band, the system changes over to the NV0 state. And the green laser can actually drive both processes. It can bring it from the NV minus to NV0, and it also can go back. Now, one way to reduce at least that contribution is that instead of the green laser, we use an orange laser, so we have a lower photon energy, and that lower photon energy cannot bring the system back from NV0 to NV minus. And so we still lose some population over into NV0, which reduces the signal, but it doesn't go forth and back, and so we avoid the modulation and the loss of polarization. And that actually helps. You can see here comparison of the nuclear spin polarization for the orange laser here, that's the red symbols, and the green laser, and you see as a function of the laser pulse duration, the orange laser preserves the polarization better. Yes?
Yeah, I'm just curious, is the laser pulse itself polarized?
No.
Would it change if the laser itself is polarized?
I don't think so.
Circularly polarized?
No. I mean, we're anyway not exciting resonantly.
Yeah.
And
But I mean, even if we excite non-resonantly, still there could be some spin information transferred in those states. I'm not sure what I'm saying because I do not know the details.
yeah, nobody has seen any such effect, and it's not expected theoretically. Yeah, so yeah, maybe I should probably skip a few slides because, which means, of course, anyway, I'll just summarize that. This was basically the core of the talk. Unfortunately, I've spent too much time on on other stuff. But what I tried to show you, or what I wanted to show you, is that combining an electron spin with a nuclear spin has some interesting potential. The electron spin we always need. As I showed you, we need it for excitation, for initializing the system, and for reading it out. Also, the electron spin is nice because it is fast. I mean, it has a high interaction with the external magnetic field, with microwave field, so you can apply gate operations which are fast for magnetic resonance on the order of a few nanoseconds. For nuclear spins, the coupling strength is much weaker, and so it takes much longer to apply operations. On the other hand, you have more of them. I've shown you can have 5 spins, for instance, nuclear spins, and they have much longer dephasing times. So for instance, for use in quantum memories, the nuclear spins are really useful. But yeah, so you have some advantages for both types of spins. And the challenge that you face is that if you want now to apply gate operations to both types of spins, for instance, a 2-qubit gate, where you first initialize the electron spin into a certain state with this pulse, and then you apply a gate operation on the nuclear spin. This gate operation can take on the order of 100 microseconds. Unfortunately, the electron spin dephases on the order of 10 microseconds. And I show you here the result. So you expect, as a function of this radio frequency gate, which drives the nuclear spin, you expect to see an oscillation. This is a Rabi oscillation of the nuclear spin. That's what you expect under ideal conditions. In reality, what you see is just a decay, because the electron spin dephases. It doesn't have enough memory time. So if you want to see something, that's because this electron spin is in a coherent superposition, which dephases. So if you want to get a good operation, you have to do a so-called protected gate. You have to rephase this dephasing, and what you use here is again something that was first discovered in NMR. You apply echo pulses. So you refocus the coherence in a scheme which is called dynamical decoupling in the context of quantum information. And if you do that, then you can get an almost ideal gate operation. But there are other issues. One thing is that we apply here a very strong radio frequency field. I mean, because the nuclear spin is 1,000 times weaker than the electron spin, you need to drive it pretty hard to get even a 100 microsecond gate operation. And the electron spin, of course, sees that radio frequency field also. It's very far off resonant. But there are second order effects which are non-resonant, and so you get here what's known in NMR as a Bloch-Siegert shift. And this Bloch-Siegert shift can again destroy the coherence in the system. That's one problem that you have. I don't want to show you the result here, but what I try to show you is that there are problems when you apply radio frequency fields. One problem is the gate is too long. You also have to excite many frequencies. I mean, if you look here at the carbon-13 spectrum, it's split by the hyperfine interaction. And the hyperfine interaction is on the order of 110, 150 kilohertz. The whole spectrum can be more than 300 kilohertz wide. And it's absolutely impossible to drive a carbon-13 hard enough to excite all these transitions. So this is apparently not the way to go. And instead of trying to apply such hard radio frequency pulses, we have decided to do without radio frequency pulses. We use what we call indirect gate operations. Instead of driving the nuclear spins, we only drive the electron spins. But flipping the electron spins modulates the hyperfine interaction, and the hyperfine interaction then drives the nuclear spins. It's a bit more challenging because you cannot just generate a single pulse, you have to generate a sequence of pulses, but the resulting gate operations are better. They don't have these side effects, and they are faster than the direct excitation. So instead of requiring, for instance, 100 microseconds, we can do it in 10 microseconds or less. So that's the so-called indirect control operation. I have to skip a few slides again and just show you one result from that for a specific reason. This is the so-called quantum speed limit. In the context of quantum information processing, this is a question which was often asked: how fast can a gate operation be? And there's in principle a very simple rule, which it's basically the inverse of the energy in the system. It's very simple to see. If you look at the spin 1/2, you want to bring it from 0 to 1. That means you have to rotate it by 180 degrees. And the time that is needed for that, this is a not operation, the time that it's needed for that is pi over the Larmor frequency. So it's inverse proportional to the energy, the Larmor frequency, is the energy of the system. So that's for a single qubit. In the case of 2 qubits, you can do something similar. Again, I'm looking at this hybrid system. In this case, we want to drive the carbon, the difficult one. So we use the electron spin as a control qubit and the carbon-13 as a target qubit. And now the energy scale, if we don't use a radio frequency field, the energy scale for the carbon is given by the hyperfine interaction. So that's now the strongest interaction, and that's why we can be relatively fast. In this case, the hyperfine interaction is 110 kilohertz, and that tells you that the minimum time that we can for this control knot operation is 4.54 microseconds. Again, you have to compare that to 100 microseconds if you use a radio frequency field. And if we do that, again, this is the system that you've seen you already. This is the control qubit. The electron spin is in the state 1, logical state 1. The target qubit is initially in the state 0. And now we let it precess, no radio frequency field, just free precession under the effect of the hyperfine interaction. And you see, to get from 0 to 1 takes, in this case, about 4.54 microseconds. So we saturated the quantum speed limit in this case. And of course, you have to check that the state is correct. So you end up in the state 1-1. You start in 1-0. You apply a control knot, so you end up in 1-1. And you should also check what happens if the control qubit is in state 0. In this case, there is no precession, and at the end, it stays in the state 0-0. So that's the quantum speed limit. And the reason I wanted to show that is that paper appeared yesterday. I had planned to put it in the presentation, but I was a bit more motivated. So let me come to the conclusion. I mean, I tried to show you that we can use these hybrid quantum registers or quantum registers in general. And I hope I've been able to convince you that in principle it's possible. But whenever you do something like that, people will immediately ask, but is this useful? Now, since this is what the quantum hub was the name, right? So I'm sure you're all convinced this is useful, but let me anyway give you some more arguments. And we all know that there are some quantum algorithms which have been discovered 20 years ago or 25 years ago, like the Grover algorithm. But to be honest, I mean, who's really interested in searching a database with a quantum computer? There is Shor's algorithm, which is much more interesting in the sense that the speed up is exponential and not quadratic. So, but on the other hand, I mean, how many of you really want to find prime numbers? So, but I would say there are some applications which are really interesting, at least in my opinion, which are, for instance, simulations of quantum systems. I mean, we're physicists, and so all of us have tried to simulate quantum systems, and we know this is a hard problem, and we know that quantum computers are really predestined for that. I mean, Feynman was the first one who discussed the option of using quantum systems for simulating other quantum systems. So this is a really interesting application, in my opinion. And this is something that we started, I would say, 23 years ago. You've been working on that also for some time. And I would like to show you one example, which was not done on this NV system. This was done with nuclear spins. But this is a simulation of a quantum system. I mean, it looks probably too clean, but it's an experimental result. So we prepare a quantum state which is located on 1 qubit. And then we let it evolve under a certain Hamiltonian. I don't have time to go into detail, but you see it spreads. And I mean, this is what you expect for many systems. For instance, if you have a photon, you localize it in space, you know, it will spread. And many systems are delocalized. And in this case, also, the eigenstate is completely delocalized. So as a function of time, the size grows. Now, we know that many systems which are in the ideal case delocalized are in practice localized. And this has been an old problem which has been discussed in many different contexts. And it turns out one reason why they localize is that there are perturbations which prevent it from spreading. For instance, in some solids, the electrons are localized and so they become ice insulators as a function of doping, for instance. And we can simulate that with this nuclear spin system. You see here, when we introduce a perturbation, which is sort of the analog of the doping, actually the spreading slows down and it comes to an end, so the system reaches an equilibrium size. And if you can repeat that as a function of the perturbation strength, and what turns out is this a very clean example of a quantum phase transition. As a function of the perturbation strength, you have a delocalized phase and a localized phase. So and you have this so-called critical behavior with the critical exponent and so on, which is basically a textbook example of localization, but was done experimentally. And this is something that you cannot do on a computer. This was done with approximately 7,000 nuclear spins. So it's a quantum register with 7,000 qubits. It's a quantum simulator because we cannot control the individual qubits. But that's not necessary for this simulation. That's the difference between a special purpose quantum simulator and a general purpose quantum computer. So we cannot solve the Shor problem here, but we can do this quantum simulation. And for that purpose, it's an extremely powerful system. And in my opinion, it's more interesting than finding prime numbers. And if you're not convinced by that, I'll give you one more example, and then I'm finished. I mean, if you look at the internet, what 90% probably of traffic in the internet is images, movies, graphic information, right? So if you can find an application which improves the storage, transmission, and computation of graphic images, then you definitely have an application which is useful for everybody and not just for physicists, right? And so this is an example of an image, and we would like to do that, to do some processing of it. And these processing steps are normally mathematical operations. You can represent them as matrix operations. And for instance, one of them is called a Hart transform, which transforms this image into that one and vice versa. So if you want to do that on a computer, you have to do three things. You first have to encode the image. Then you have to process, which means the matrix operation, matrix multiplication, and then you have to decode the image, the transformed image. So if you do that on a classical computer, say you have 16 megapixels here, which is typical camera size, then you need, of course, if it's black and white, you need 16 million bits. And you have some matrices here, which are then the same order of magnitude. So yeah, you need 10 to the n, which is in this case 16 million bits. If you do the same thing on a quantum computer, it turns out instead of 16 million, you need 24 qubits. So obviously you can greatly reduce the requirements, and you may believe me that the transformations that you generate then, the mathematical operations, are also a lot faster. But to give you the extreme example, this is typical image operation. You have a black and a white area, and the goal is to find the border between these two areas. So it's called edge detection. Now, if you do that on a classical computer with 16 million bits, you need roughly 16 million operations. When you just compare neighboring pixels, and if it changes, then you have a border. Turns out on a quantum computer, once you have done the encoding, it takes one operation on 1 qubit. So independent of the size of the image. So this is obviously a very efficient operation. If you're interested in details, you can read it up here. And so in my opinion, what I try to show you is there are interesting applications for physicists, for people who want to crack codes, but also for everybody in the whole world, I would say. I mean, maybe not interested in cats here, but anyway. So, and the fact that there is a potential for such applications is driving now an industry. This is an overview how industry has started to pour money into the field. And this is an overview of some of the companies which have sprung up over the last years, developing hardware, software components, applications, or full stack applications. Some of the companies you will know, others maybe not, but there's a lot going on in that field. So I come to the conclusion, sorry for the delay. What I try to show you that computers based on quantum systems can be very powerful. I guess you knew that it's not so easy to realize that potential. I guess you also knew that. And then specifically that quantum registers based on different types of qubits are interesting. The indirect control part, unfortunately, I didn't have much time to show, but I hope you remember that diamonds are our best friends. Thank you for your attention.
Silicon carbide,
yeah.
second best friend.
Maybe, yeah. I mean, it's very different. Diamond we know very well, and we know how what the advantages, disadvantages are. Problem. Silicon carbide we're still trying to find out. And for instance, of course, there are really thousands of potential centers, and we won't have the opportunity to find the best one. Particularly not before my retirement.
Just to continue on that, so one of the complaints we have on diamond system is that we still don't have the technology to engineer the centers. So what's your take on that?
Well, I mean, it's something that I'm not interested in, but I know that very many people are working on that. I hope they will find a solution. I have seen probably dozens of proposals over the years, and some of the companies I mentioned are betting on that they will be able to do that. It may be easier in silicon carbide, but as far as I know, they also don't have a solution there yet. I mean, it's becoming more realistic if you have a technology which can use techniques developed for silicon, because in silicon they are now really the precision of a few nanometers, 1 to 2 nanometers can be reached on silicon. And maybe that can also be applied to this type of systems.
Any questions over there? Maybe one or two more questions.
So is this hybrid qubit scalable easily beyond 2 that you showed?
Well, in principle, there is no limit, but it's basically what he's saying. It's challenging. There are one way is, of course, to implant more centers, and some people are also combining, so you have a local node which has just a few qubits, maybe 5 qubits, and then you connect it by an optical fiber to a different one. But again, diamond is not ideal for that because the transfer from stationary qubits to flying qubits is relatively inefficient. But silicon carbide might be better suited for that.
Go to the slide before the application started actually.
Yeah. Mm-hmm.
So where you showed
The bar graph of the population.
Right. Yes. Mm-hmm. This one?
So what is the negative population actually?
This is just error bars, basically. I mean, the error is mostly because of the Poissonian statistics of the photon counting. And so in principle, we could reduce it, but we would have to count longer.
Okay, so basically statistics have been used for something, that's why we are getting.
Yes.
Okay.
Yeah, we don't have negative probabilities. You're absolutely right.
So I think if there are no more questions, let's thank Professor.